Hello, everybody. In this video, I'm going to go through how to solve uh, a projection of a vector on a subspace and its complement of the subspace. This is related to the linear algebra course in mathematics, specifically Math2099 to 501 at University of UNSW. Now, let's start to remind ourselves what was the orthogonal complement of a subspace of a vector space. V is a vector space and W is a subspace of that vector space. Now, orthogonal complement of W, the subspace W, is defined by all the vectors in V such that when we dot product, this in general form will be the inner product with the all element of our subspace. So as you know, this should be related as a vector there. Okay, so in basically our examples are in the Euclidean space. We are dealing with the R to the n type of R to the 3, R to the 4 type of vector spaces for simplicity, but in general form, this is a orthogonal complement of a subspace if the space has an inner product, and then you change the inner product with the dot product. Here you will get exactly the same definition. How we think about that, how we visualize what is the orthogonal complement spaces, I usually give to my students that if you're on the floor, right? Each of you is normal for this floor. So the each multiples of you, every normal vector, every multiples of the normal vector, also the negative of them is the complement of the floor. So floor is the W vector subspace in the three-dimensional space, and W complement of the W, which is W complement, is this all these red infinitely many vectors, perpendicular vectors to the W. That is the orthogonality come from, because every vector in W complement is orthogonal to W. That's what it's all about. Okay, now the main subject for this video is to look at any vector like V here and look at the W1, which is the projection of V on the vector space W. But also we have a concept, you can think of the V as a projection of the space, the complement space, W complement. In this case, you will have the vector like a W2, and they are connected together. And this is the subject for today's video. Projection of a vector on W and W complement. Now assume we have a basis, whatever your dimension is, B1, B2, Bm. So this is the m-dimensional subspace, and this is an orthonormal basis. If you have an orthonormal basis, which means that if you multiply any two of those vectors, you will always get 0. If you make the dot product with itself, you will get 1, because it means that the length of those vectors have 1. These are the unit vectors, and they are perpendicular together. So that's what orthonormal basis means. Projection of a vector x on W will be given in this formula, but this formula works only for orthonormal basis. If you have an orthonormal basis, then this formula is valid. If you want to ask to the projection of the vector x or vector v, I've denoted here v, vx here in the w. If you want to look at the w2, what is w2? Will be, of course, x minus the projection of w. This is consistent with this observation, right? Because this is w1 plus w2 will give you v as a vector summation. We know how to add the vectors. W1 plus W2 will give us the V. So if you want a W2, W2 will be the W1 minus V, minus the projection of V on W. That's exactly what this one says, right? This one says. basically as a vector, if you look at the shape, then this will be the projection of the vector x on W plus the projection of the vector x on W complement will give you the vector x. That's just, this one is just a vector addition, it's nothing else. This part is a term, this part is a term. Here, as we realize that this vector is perpendicular to W, so it is in W complement. And if we want the projection of W on X, also we can establish in a matrix form, if put the Q matrix and all the columns consist of those orthonormal bases. Orthonormal bases, it means that that will be an orthogonal matrix. And QQT will give you a symmetric matrix. And symmetric matrix means that the transpose is equal to itself, or P squared is equal to P. So you can obtain a projection map transformation with this way. So projection transformation is Q transpose. Let's do some exercise to clarify what is happening. So we have a vector V is given to us. We have A1 and A2, and the W is a subspace spanned by A1 and A2. We want to find out the projection of V on W. We want to write down V as a sum of W1 plus W2. W1 is in W, and W2 is in the complement of W, is in exactly the same way on the floor or on the floor or up the floor, on the perpendicular places of the floor. Now use this B, we would like to find the shortest distance from the point 381. The 381 is the tip point, end point of this vector, to W, and we would like to use the B to find the reflection of the vector V with respect to the plane W. So W will be the mirror, and we will look at the reflection. Okay, now first thing first, if A1 and A2 are linearly independent, then they are bases, right? And they are linearly independent because they are not multiple each other. If you have two vectors, it is easy to check whether they are linearly independent or not. If they are, there is no lambda in R such that the lambda A1 is equal to lambda times A2. There is no such lambda, right? This is not a multiple of this. Impossible. So they A1 and A2 vectors are linearly independent. This means that A1 and A2 is a basis for W. Okay, that's good. Now, the theorem tells us in order to be able to find the projection, we need orthonormal bases. So we need to look at the dot products of A1 and A2 all possible ways, such that to see whether it's an orthonormal basis or not. We know now it is just a basis. We don't know whether it is orthonormal or not. So we need I always advise to do this with a table. If you do it with a table, like a dot product here, you have vector A1, A2, A1, A2, and look at it. You don't need to calculate here because dot product is commutative. So A1, A2 is equal to A2, A1. So this has to be equal to that one. So if you look at the A1 and the length of A1 basically will be 2 squared plus 1 plus 2 squared square root. And that is, if you look at the dot product A1 times A1, that will be 2 squared 4 plus 1 squared 5 plus 2 squared 4. That will be 9. So that's 9. So A2 is 3 squared plus 1 squared plus 0 squared. 6 plus 1 is 7. That's that. And A2 will be 3 squared. Sorry. A1, A2 will be 7. 3 times 2 is 6, and 1, that will be 7. This will be 3 squared, 1 squared, that will be 9 plus 1, that will be 10. So as we see, this is a basis, but it's not orthonormal, because if it's an orthonormal, I would have 1 here, and 0 here, 0 here. Okay, So that's what I say here. Orthogonal means that if you multiply, if I dot product any two non-different, then I will get 0. If I dot product by itself, I should get a number. That's an orthogonality. And if I dot product, if the length of those vectors is 1, then I have orthonormal. So for example, E1 and E2 are orthonormal bases. They are perpendicular together and also the length is 1. Okay, what we learned from last week, how to, if you have any basis, we can always obtain an orthonormal basis by using the Gram-Schmidt process. So that's what we're gonna do. We need to use Gram-Schmidt method to find out an orthonormal basis so that we can use the projection formula to calculate the projection. That's the aim of the game. Okay, the vector, the Gram-Schmidt process, basically it is a recursive process, give us the way to find out the orthonormal basis. It says first vector will be the first, V1 is equal to A1. The second will be the A2 minus the projection of the vector A2 on the vector V1. We know this formula from the last year, so that will be a multiple of the vector A2. That will be, so A1 is V1, so this is V1. So I wrote it A1, V1 here, but this is basically V1. So it's a multiple of V1. So this is why we have V1 times A2. It appears only A2 here as a dot product here, and this is a multiple of V1. And V1 is equal to A1. So that's the definition of the projection. Calculate the dot products, so plugged it in. So that will be A1, A2. We calculate 7. A1 is 9. A1, A2 is 7. So this is 7 over 9, A1. So this one will be A2, which is A2, this vector, minus 7 over 9, A1, 2, 1, 2 is the A1 vector. This way we calculate this vector will be the vector V2. So you have V1 vector and V2 vector. V1 vector and V2 vector will be an orthogonal basis. So this is what I'm saying here. In that moment, you have an orthogonal basis. Now we calculate normalize. Normalizing means that we will calculate the length of these vectors and divide their length to its vector to find out the length of the vector that we found is the unit vector. Is the length is 1 unit. Okay, so U1 will be V1 divided by the length of V1. So this vector is unit vector in the direction of V1. U2, similarly, V2 divided by the length of it. We know how to calculate the length, right? I don't need to repeat it. So if you do that, just here, the blue section shows you that U1, the length of U1 is 1. And because this will always be true, because if you take the length of this vector here as the length of this vector, this is the green thing here, then always you will have length of V1 divided by length of V1, it's always 1. So this formula always gives you a vector of length 1. So this is what I'm saying in the green section, and the blue section tells that the length of U1 is 1 in a way. So, sorry, I don't need here I only need 2 lines and not accidentally it became 3. Okay, now we calculate U1 and U2. Now U1 and U2 orthonormal bases. It is better to check all the time our calculations. You can quickly check that whether this is the form just by maybe multiplying U1 times U2. If you do that, it needs to be 0 because of the orthonormal basis definition. just checking your calculations in your problem solving situation. Okay. Now W is spanned by A1, A2. This is the any basis. V1, V2 is the orthogonal basis, and U1, U2 is the orthonormal basis. And the theory tells us that projection of the vector x on the vector space W is given by this formula. You calculate the vector times the dot product of U1. That will be the multiple of U1. There's a coefficient of U1. And the coefficient of U2 will come from the dot product of x together with U2, dot product of x with U2. Now, it is a straightforward. We can calculate it. We know how to calculate the dot products. This is just the numbers that you can come up with. So that's, and in the end, you will find a vector, and that will be, we call it W1. 5, 2, 2, you found it. So this is W1 is this vector. W is the plane, and W complement is this perpendicular vectors perpendicular to the plane. And the vector x, the projection of the vector x on the vector space W is the vector W1. So this is all I am saying here. Now, the B section says that every vector can be written as a linear combination of those two. So this is what we see here, right? This is the plus x, vector x will be this vector plus this vector. Basically, W1, if you call this one W2, which is basically this blue vector is really the projection of the vector x onto the complement space of W, which we call it W2. As time this plus this will give you this. So this is what I'm saying here. That's nothing else, right? That's x or v, whatever. I think I messed up in this equation x and v in several places. X equal to v in this example. Okay, then W, we can calculate each of them. This is W1, and we can calculate a W2 as a vector, as numbers. So V minus W1 will be this vector. So this vector is the projection of the vector X or V on the vector space W, which is this vector. Okay, this is all good and straightforward up to now. And now let's have a look at the shortest distance. Well, shortest distance is always a perpendicular distance. That is basically this distance, right? The distance of the W2 will give you the shortest distance. That's what I'm saying in the section C. Calculate the distance in W2 will give you the shortest distance. And this is a vector. The length of the vector will be square or square root of the square of each component, 2 squared, 6 squared, plus 1 squared. That's that one. Because that's W2. That's the length of the W2. This is the shortest distance. No problem. Okay, the reflection of the vector. So this is the vector, and we would like to find out the reflection of this vector with respect to the W plane. So this vector, which is W2, as we know, this distance should be exactly this distance here. Again, this is perpendicular. This is perpendicular. Now, the reflection vector of V will be this red vector over here, which is TW. TW is the reflection point. I mean, if you want to make the reflection to this point, or this vector to this vector was the reflection. And so this is since this is the picture, we can write it down, and this is like an equation in a sense that because TV minus W1, right, TV minus W1 will give me this distance, the yellow one here, and that will be equal to the W2, which is really the negative of V minus W1. So that's the equation. Or you can directly write it down in that way because, well, from here you will be able to get this. Or you can rewrite that W1 minus the W2 will give you TW. So you can write this one directly from the vector equation, vector addition equation from here. This one directly is perfectly fine, or you write it down this and produce this equation and then use this equation and find this. It's perfectly fine. This one or this one gives you exactly the same result. So the reflection will be W1 minus W2, which is this vector. You can also calculate the reflection by using a formula which is given to you in your lecture. So this is the formula for the reflection map in the plane W. Call this map is R, so that's a matrix. And this is an identity matrix. Identity matrix, whatever the dimension here, we are dealing with the three-dimensional Euclidean space. So this is 3 by 3 identity matrix. And D is the vector, which is W2 that we talked about, -2, 6, -1 in our example. Now, this is a dot product of this vector that we call D. D is the shortest distance. That's what it represents. And this is the D dot D transpose, which is the matrix multiplication. Now, this is a formula for calculating the reflection. So let's calculate this in our example. The task is basically this part. So if you calculate D dot product D, will be -2, will be -2 times -2 will be 4. 6 squared is 36. 1 squared is 1. So this is that number. Now you have a D, this is D, and D transpose is this one. So multiply this one. So this is the 3 rows, 1 column, and you have 1 row, 3 columns. So when you multiply these two matrices, you will have 3 by 3 matrices. This times this will be 4. This times this will be -12. This times this will be +2. And so on. That's a matrix multiplication as you practice row by column. This one, and so on. And you have an identity matrix here. Identity matrix means this the 1, 1, 1 in the diagonals and the zeros elsewhere. So this is a subtraction that you need to do. The numbers that will change will be the diagonal ones. So that's what I've done in the corner to ensure you these are the coefficients. That's the diagonal entries numbers are coming from this calculation. So this is R. This is our reflection formula, reflection transformation. That's what we talked about, the T here. The T here in general form, regardless of the vector, is T. If you want to calculate the V, you will calculate, put a V here and just multiply those numbers. I haven't done it, but that's what it is. So that's another way to look at the reflection formula. You need to know it. Quickly, another example. This will be in the same line. In this case, we have W. V is a vector, and W is again a plane, but this time it's given by an equation, a plane equation, x minus 3y minus z is equal to 0. We want to write it down a basis for the complement. Find the projection of V onto the complement. Find the reflection of V in the plane W. Now, W complement, if you have a plane, we know that W complement is really generated by any normal. So basically what we want in the first section is to see what is the normal of this plane. Those are the coefficient vectors, right? Coefficients of this one will give us the normal vector. That is 1 minus 3 minus 1, right? 1 minus 3 minus 1 will be the normal vector, and the orthogonal complement will be spanning by this normal vector. Now, a normal vector is a basis for the complement, and it is if it is, it is one vector, so there is no other vector we can check the orthogonality. It is orthonormal because um, there's one. But you need to make this vector into unit vector. So this is why we need to divide into its length. Don't forget this step. This step is really important, as we really, as I said, previous sessions, orthonormalization in Gram-Schmidt method is extremely important. Orthogonality is not enough for these theories that we set it up, because orthonormal basis corresponds to orthogonal matrices. Orthogonal basis does not correspond orthogonal matrices. Okay. So normalization is important. So we need a unit vector. So we need to divide this into its length. So that is the vector. Now we have this one, which is the unit vector. That's the basically orthonormal basis for us. So the projection onto the space W complement will be just the usual projection. You have only one vector, so this is the unit vector, and the unit vectors dot product V. So let me show you the formula again. So this is what is coming, where it is coming from. That's exactly, but in this case, you have one vector, which is the orthonormal vector. So this formula will be only this part, right? Your dot product and itself. So that's what I am doing here. Right? The projection will be the basis, dot product, the vector V, and the basis. That's and then you calculate that number, calculate the dot product, calculate, then you will find this vector. Okay, and this is the calculation that I've done here. And the last part of this question says that the reflection of V into the plane W with respect to the W. Same idea in this question, but I calculate the reflection by using the reflection formula. D is the unit vector. D is the W2. D is the normal to the plane one. So D here will be 1 minus 3 minus 1, but in the maybe I should have called this one. This was the normal vector. So the unit vector corresponding to this one is this vector, which is 3 minus 9, 3. But if you take the 3 out, so you have 2 here, n dot n will be 11. So that's 11 here. Then you have 1 minus 3, 1. And then you have the transpose of this one. And then you calculate this multiplication, this identity matrix here. This multiplication will give 1 minus 3 minus 1. You will have minus 3, 9, and 3, and so on. So you will have this matrix. And then R will be this matrix. And then V was this vector. Multiply this matrix with this vector will give you this reflection. So 1, 10, 4 is the reflection vector for the vector reflection of the vector V with respect to the plane W. So that's your answer. It was easier to use this R reflection formula in this question rather than to go through the other way around. because it is already given to you. D is in the W hat, and the W hat has only one basis element. So was a lot easier to use this one. It's more quicker. So so it's the best for the question is advisable to use, especially when you're doing your assessment, you are facing with the time issue. Hopefully this is helpful for you, and thank you very much for watching. All the best. Take care.